So let's start by setting up our component equations. X equals V naught times cosine of theta times t, and y equals negative 16t squared plus V naught times sine of theta times t plus the initial height of 5. We do not have theta, so I leave it as such. Why don't we begin by expressing interest in when the ball hits the ground. Now, we hit the ground when our height y is 0. So I'll put a 0 in for y. And now we need to find the value of, or the values of t that make this true. So this is a quadratic equation, equals 0. It's a quadratic equation. So I'll remind you that this is A, that's B, and that's C. So what we can do is we can set up the quadratic formula. But now notice that the issue here is that we do not know what sine of theta is. If I knew sine of theta as a number, I could plug in that number here and here, and I could turn all of this into a number to find the time when our football hits the ground. So for now, I got to take a time out. We'll come back to this in a moment. For now, let's go play somewhere else. For now, we will consider the fact that the maximum height is 21.44. The maximum height happens at time the opposite of b over 2a. So let's consider what this is. And of course, we're looking up here now because we're talking about the height. So the discussion is with the y component, the vertical component. So let's go negative b over 2a. So the additive inverse of b would be negative 46 sine of theta over 2 times a, which can become 23 over 16 sine of theta. So this here, that is a t value, right? That equals the t value when we reach our maximum height. But recall that for this function here, the coordinates are not x and y. The coordinates are t and y. At a specific time, you have a specific height. So here at this specific time, my height is that. So what I'm going to do is I'm going to access this function where instead of time, t, instead of t and t, I plug in this. And instead of y, I plug in our maximum height because our maximum height occurs at this specific time. So let me plug in this and that into that and that. And now I look for opportunities to reduce. So maybe I can subtract the 5 to this side. Maybe I can clean up these exponents, and maybe I can clean this up as well. Now these actually are like terms, so you can combine them by adding their coefficients. And now I'll multiply by the reciprocal, and then I will square root. And this leads me to discover that sine of theta equals 0.705. So from all of this, I discovered the fact that sine of theta equals this. Now we can resume to play back over here because recall in our quadratic formula, we just needed to know what sine of theta was. So now that I know sine of theta, I can make this substitution back in here and back into there. And now we will go ahead and simplify this expression. We will apply the plus and minus to get two different values of t. So I have discovered that there are two times, but we discard the time that is negative, and we only run with time 2.17. And recall that this time is the time when the ball hits the ground. So I can take this time and I can plug it into this component. Now I'm going back to the x, because x represents horizontal, and the overall goal was to find w, which is how far away the ball landed from the football player. So 2.17 goes in for t. Now as for cosine theta, I need to know theta. So what I can do is I can actually go back over here. And what I can do is I can take the sine inverse of both sides. So that theta is the sine inverse of this here. And this tells us that theta is about, let's say, about 44.83 degrees. So that was the initial launch angle, theta, which was not given to you at all, but which we just found. So with this theta value and with this time value, we can go back over here. And so we have our final answer, 46 times the cosine of 44.83 times that by 2.17. And that should be about, it's awfully close to about 71 feet. So was it a lot of work? Oh, it sure was. But that's how a problem like this can be approached.